when will we continue to use things? I am actually reviewing partial fraction decomposition with my second year calculus students because we have to use it in our calculus work today. So I'm teaching partial fractions in this class and in calculus today. It's kind of funny that they overlap to be the same day, but okay, so yesterday in your notes, you looked at these, whether you wrote them down or not, I don't know, okay? But when we have a fraction that we want to decompose, okay, that sounds like kind of a morbid word, but when we talk about decomposing, what does that mean? Like to break apart, right? So we're taking a fraction and we're breaking it apart as much as we can. All right, so your first step was to factor the denominator. And then we had these rules, right? If it was a linear factor, then we had a number on top. If it was a repeated linear factor, then we needed all of those. And if it was a quadratic factor, we needed a linear numerator, okay? Now, moving forward, after we have the setup, okay, what you are going to do is you are going to multiply both sides by the least common denominator, okay? We're going to have an algebra problem now. We're going to multiply both sides by the least common denominator so that we no longer have any denominators. Then we're going to actually have to solve for A and B, potentially C, potentially D. I don't know, maybe it's going to be crazy. You have an E there also. Okay. But we're going to have to solve for all of those values. There are going to be two ways that I show you how to do this. Okay? The first two examples, I'm going to show you what's called substituting zeros. Okay? The second two examples, I'm going to show you how to compare coefficients. I know that means nothing to you right now, but it will here pretty soon. So we're going to do 4 examples. I didn't have you set up the fourth one. We're going to do 4 examples. The first 2 are going to substitute zeros. The second 2 are going to compare coefficients. And then our last step will be to actually write out the decomposition. So we solved for A and B and C, etc. Now let's go back to the setup of the problem and actually change A to the numeric value that we solved for, and change B to the numeric value that we solved for. So we're going to do 4 examples. We've already set 3 of them up. I'll talk through them again as we do it, okay, so to re-emphasize why we're setting it up, what we're doing, okay? And I know it feels random that we're talking about fractions in the middle of our linear systems chapter, but here when we get to the 3rd and 4th example, you'll kind of see why we're doing it, okay? All right. Are we ready? Okay, let's do some algebra. Okay. So the first one we talked about is this one. So either you already have it written down or you have to rewrite it down. I don't know. Okay. But what we did in our warm-up is we factored this to be x plus 4 times x plus 2. And since there were 2 factors, we broke this up into 2 fractions, where the first fraction had a denominator of x plus 4, and the second denominator had a fraction of x plus 2. Okay? Now, if you set this up flip-flop, that is fine, but if you want to follow my work, you're either going to have to understand that A and B are going to be switched for you. If you think that's too much for your brain to keep track of, then set it up like we did up here. Okay, where A is above x plus 4 and B is above x plus 2. That's how we set it up, right? Okay. All right, so once we have our problem set up, we are going to multiply by, we're going to multiply by the least common denominator. And your least common denominator is always going to be this denominator right here. Whatever your original denominator is, that is what you're going to multiply by. Okay? So we are going to multiply by x plus 4 times x plus 2. Well, what happens when we do that? Bless you. When we multiply x plus 4 times x plus 2 to this fraction, it cancels out the entire denominator, right? And so we're left with the numerator of x plus 8. What happens when we multiply the LCD to this fraction? What cancels? The x plus 4 is canceled. So a is left to be multiplied to x plus 2. What happens when we multiply the LCD to this last fraction? What cancels? The x plus 2's cancel, which leaves b to be multiplied to x plus 4. Okay, now we've gotten rid of our fractions, which is nice, and we can now solve for a and b. Okay, so the first method I want to show you is substituting zeros. We are going to strategically pick numbers to help us solve for a and b. Okay, let's talk about this factor right here. What could I plug in for x to make this 0? Okay, well, let's try that. If I plug in x is -2, we would get -2 plus 8 equals a times -2 plus 2 plus b times -2 plus 4, right? I'm plugging -2 for anywhere there's an x. Well, what happens right here? This is what?
0.
That was the whole point. What's 0 times a? 0. So this goes away, and we're left with positive 6 equals 2b. So b equals 3. Okay. What is another value we could strategically choose to plug in for x? If we want this to disappear, we could plug x equals -4. Right? So we can plug a -4 anywhere there's an x. Okay? So we get 4 equals -2a, and this goes away. That was the whole point. Okay? All right, so what's a? And those are the two numbers we needed to solve for. Okay? So now we can go back to the very beginning, and we can say that our x plus 8 over x squared plus 6x plus 8 equals a over x plus 4 plus b over x plus 2. What do you think? Okay. I like this method. We're plugging in numbers to make a factor go away, and it makes everything nice, right? Okay, we can solve for that one letter that's left over. Okay. Now, this was nice because all of our denominators were linear, and none of them repeated. So this process went very, very smooth. Okay. Let's look at what happens when we have that repeated linear factor and how that might put a kink into this method. Okay, not a big kink, a kink that we can work through. All right, but it's going to present one challenge for us. Okay, so this was the second example that I had you set up in your warm-up. Okay, we decided that this denominator factored to x times x plus 1, the quantity squared. So the setup that we used was a over x plus b over x plus 1 squared plus c over x plus 1. Since we have 3 factors, we have 3 fractions. Since all 3 are linear, then we have all 3 numerators are just a number, just a constant. Okay? But since we have a repeated factor, keep in mind that each version needs to be in there. So x plus 1 to the first power and x plus 1 to the second power. Okay? I know that some of you look at this and think, but this is a quadratic. If we multiply it out, you're right, it is a quadratic. But since it's a repeated linear factor, we treat it as such, a linear factor. Okay? Are we all okay there? All right, so now we're going to multiply. We are going to multiply by our least common denominator. And that is always going to be whatever this is right here. Okay? Our goal is to get rid of our denominators. Okay? So this is going to happen every time when we distribute to the original fraction. This that we're multiplying by is the same as the denominator. So we are going to be left with just the numerator. Okay? What cancels out when we multiply it to this a fraction? Okay, only the x is going to cancel. And so a is going to be left to be multiplied to x plus 1, the quantity squared. Okay. Here, when we multiply to the b fraction, both x plus 1's cancel. So we can write b times x. Okay. And then when we multiply to this fraction right here, only one of the x plus 1's cancel. So c will be multiplied to x and one of the x plus 1's because the other one canceled, but not the second. Yes?
What is that third x plus 1 under c?
This one? Mm-hmm. Okay, so since we have a repeated factor, we have to break it up to where we represent each exponent. So this is x plus 1 to the first, and this is x plus 1 squared. Okay? If we had x plus 1 cubed, we would have an x plus 1, an x plus 1 squared, and an x plus 1 cubed. Okay? Yeah.
Does squared have to go first, or could it be like b over x plus 1 plus c over x plus 1 squared?
That would be perfect. Okay? Remember, addition is always commutative. So if you set yours up in a different order, it's not a problem. When we get to the end, the right numbers will be over the right denominators. Okay? Your b will just be different than my b.
But it'll be correct because it has a different denominator, right?
Yes.
Okay.
Mm-hmm. Yes. Okay, so now let's use the method that we were doing. What is a number we could plug into x that would be very helpful for us? -1. All right, we have a factor of x plus 1 that appears a couple times. So let's plug in -1. Okay. And some of you are going to be able to do a little bit of this in your head, but when we plug in -1 on the left side, We have 5 minus 20 plus 6. What would that be? Negative 9. Okay. And then it looks like we have A times 0. We have B times negative 1. And then we have C times 0. Okay. B is 9. What is another value for x that we could plug in to help us find a constant?
0.
Okay, we have a factor of x, so plugging in 0 is going to be helpful for us. Okay, now plugging in 0, I think we can do some of that in our head, right? What happens when we plug in 0 to this left side?
It's just 6.
We get 6. Okay, and then we have a times 1 squared plus b times 0 plus c times 0 times 1. So really we get a equals 6, right? Over here we get 6. Here we get a times 1 squared plus b times 0 plus c times 0 times 1. Okay. Well, what about C? Technically, we've used all of our factors, haven't we? And this is our key. How are we going to figure out C? Okay. Do we know A and B? So if we plug in A and we plug in B, does it really matter what we plug in for X? Okay, we can choose a different number for x, knowing that we have all of the other constants, right? So let's think of a number that would be really easy to plug in that was not negative 1 or 0. 1 is a nice number to plug in, right? So if we choose x equals 1, and I'll scroll down a little bit for us here, then we get 5 times 1 squared plus 20 times 1 plus 6. We know that A is 6. We know that B is 9. And so when we plug all of those values in, the only unknown is our constant C. So what do we have right here?
31.
31 equals, this is 6 times 2 squared, 24 plus 9,
33.
plus 2c. So Reagan, coming back to your question, if you set it up the way that you are saying, your B would be the negative 1 that we just found. Okay. All right. Hey, we have all of our constants. Okay, so now we can come back to how we set it up. Our original problem was kind of long, 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x. This can break apart into a over x plus b over x plus 1, the quantity squared, plus c over x plus 1. Now, since c is negative 1, instead of writing plus negative 1 over x plus 1, I'm just going to write it as a subtraction of 1 over x plus 1. Is that okay with you? And there we are. Okay. When you have linear denominators, whether repeated or not, this method of substituting in zeros goes really nice. Okay. There's not a whole lot of algebra that you have to do. Yes.
Since we're dealing with fractions, if we ever are able to simplify, do you want us to or no?
So, yes, I would, but I can't think of a time where that would happen. Like, it should already come out simplified.
Okay.
The only thing that could happen is if you got like C equals 9/6, and you would need to reduce that down to 3/2. Also, I don't really like fractions in a fraction. So if your A, B, or C ends up being a fraction, then that's where you would have to simplify and make it, rewrite it to look that there's not a fraction in a fraction. Okay? Does that make sense? Fractions in a fraction don't look pretty.
Are you okay with this?
No. No decimals in a fraction either. Okay? So just remember that if you're dividing and you have fractions, dividing is the same thing as multiplying by the reciprocal. Okay? All right, so this was the third one that I had you set up. Okay? So Emma, you wrote this one up there, right? Okay, Emma factored the denominator to x times x squared plus 4. Since there are two factors, we want two fractions. Our first factor is x. Our second factor is x squared plus 4. X is linear, so we're going to put just a constant in the numerator. But x squared plus 4 is quadratic, so she wrote a linear in the numerator. Okay. Oh my goodness. Okay, so our first step is to remember multiply by that LCD. Okay, some of you are going to write out this step. Some of you may think about it in your head, but at least for your notes, write it out so you have that to reference. Okay, every time you take the LCD multiplied to the original fraction, the denominators will cancel. When we take the LCD to this A fraction, what cancels?
The x.
The x's cancel, so A is being left to multiply to x squared plus 4. Okay, please be careful. Everyone look up here before you write it down. When we take our LCD and multiply it to this fraction, the quadratics cancel, which means the quantity of bx plus c, notice how I'm putting it in parentheses, is being multiplied to x. If you don't get those parentheses in, it's going to mess up everything else you do from here on out. Okay? So when you have that linear numerator and you're doing this step, make sure it gets in parentheses so you can properly do the multiplication. Okay? All right, so when you have a quadratic denominator, it really messes up us being able to plug in a number to make it 0, okay? Yes, we could plug 0 in here and figure out A, all right? But what are we going to plug in here to make this 0? Not a real number, right? Yeah, 2i would be fine, but we're not going to mess with imaginary numbers, okay? So we're going to have to use a different method when we have quadratic denominators. So for this example and the next one, we're going to use that comparing coefficients method. Okay? Look over here on the left side. we have a quadratic, right? Okay. Over here, technically we have a quadratic. What should be true about them? They should be equal, right? Okay. So what I'm going to do on the left side is we're going to actually multiply all of this out so we can see our two equal quadratics. Okay. So I am going to write this as ax squared plus 4a plus bx squared plus cx. Okay, and just for organizational purposes, so that you can see this a little bit more clearer, I am going to reorganize this. I'm going to write this as ax squared plus bx squared plus cx plus 4a. I'm going to put those terms in the same order they would need to appear in a quadratic. All of my x squared terms are first, then my x terms, then my constant terms. Okay, so this is kind of why this is in the systems chapter. What's the coefficient of x squared over here? 3. So if these two quadratics are equal, what should the coefficient of x squared be over here? It should also be 3. So my coefficients for x squared would be a plus b. Those better equal 3. Okay. The coefficient for x on the left side is 4. What's the coefficient for x on the right side? 4. Okay. So cx, c better equal 4. Okay. And then lastly, our constant on the left side is 4. Our constant on the left side is 4a. So 4a better equal 4. Okay? So we have a system of equations, but this one really isn't too bad. Okay, I think we can solve this without even a lot of work, right? What is a? A is 1. And if a plus b is 3, what does that make b? 2. And then we know that c equals 4. Okay. So our original fraction of 3x squared plus 4x plus 4 all over x cubed plus 4x would break apart into a over x plus bx plus c bx plus c all over x squared plus 4. So I call that comparing coefficients because we're taking the coefficients of x squared and setting them equal to the coefficients of x squared. And the coefficients of x we set equal to the coefficients of x. So we're taking those coefficients and comparing them. All right. One more example that's not going to take us long to set up, okay? But I do want to do this last example before I send you on your way. But hey, step one's already done for you, right? Our denominator's factored. Okay. What do we have in the denominator? Okay, we have two quadratic factors. We have a quadratic factor that is repeated, right? So we have two factors, like you said. So we're going to have two fractions. They're both x squared plus 2. So we need x squared plus 2 to the first power represented and x squared plus 2 to the second power represented. Okay, same thing with linear. Okay, if we have repeated factors, they need to be represented. Okay, but they're quadratic, so our numerators need to be linear. When we multiply by our LCD, we are going to get 8x cubed plus 13x. When we multiply by this first this ax plus b fraction, one of the factors will cancel with the denominator. So remember, don't forget to put that guy in parentheses. And then cx plus d, the denominator cancels completely and there's nothing left to multiply. Okay, now I think we're going to run out of time before we're going to be able to solve this one. But just like before, you would need to, how are you going to have to multiply this? You're going to have to FOIL this out, and then you can compare the coefficients, okay? Now, do you see an x squared over here? So what's its coefficient? 0. Okay. So I'm gonna take a time out. We're actually not gonna finish this problem, and I'm sorry if that bothers you. You can finish it if you want to. But I want to be clear. I am not here tomorrow, so you're gonna get a little bit of time to compare homework. Miss Lindsay will be here, and then your quiz tomorrow is only over partial fractions. So do your homework tonight so that you're gonna get 3 questions on your quiz tomorrow. And then Miss Lindsay will give you the review, okay? So your review is going to be 2-sided. And they're both numbered, one's 1 through 7, one's 1 through 8. For the weekend, you are going to do the front side of 1 through 7. And when you come Monday, you can ask me questions about that. And then on Monday, I'll assign you the second side, okay? So if you're not going to be here tomorrow, remember I need to talk to you like right now, okay? If you're not going to be here tomorrow,